Can you hear me now better? Yes, yes, I could hear. So Asmita reminded us that this was the day, so I have his picture in my slides, so I thought I would just bring it up. So what you have heard from Marco and Ravindran over the last day and this morning is where I actually will start. I'm an experimentalist, so you will hear in 2 lectures the experimental view of what they have been telling you, starting exactly with where Ravindran ended today. And I will use many things. You will see the same formulae, but very briefly, and I'll jump to the experimental measurement of those aspects, including parton distribution functions, various kinematics that are needed to make measurements in deep inelastic scattering, and all of that. So this is a set of 2 lectures, and I'll give them in sequence. So I'll have the 1 hour now. We'll go for lunch, I believe, and then we'll come back and I'll have the second lecture, and then Ravindran will follow in the afternoon. So I think the curiosity about what is fundamental structure of matter is universal. Studies of what is the smallest thing we can see have occurred simultaneously in the East, in the West, in their own way. And that is sort of depicted by this nice picture that was made for the Electron-ION Collider consensus report by the National Academy that blessed the collider to go forward for its science. So I'll be starting from the introduction to deep inelastic scattering in the first lecture. I will tell you what was done in the past, not just with deep inelastic scattering where the electron scatters off of a proton or a nucleus, but I'll bring in a little bit of history of the RIC, relativistic heavy ion collider, that also has polarized protons in it. Because one aspect of the EIC physics is to understand the spin structure of the proton, which we have not talked about, but I think we will go into it this afternoon. And I'll give you some introductory aspects. Every time I will end a topic in the first lecture with a question. This is the limitation of the experiment that we did in the past. What needed to happen to solve the physics problem that we were facing? And that gets motivating pointers to the future, which is the electron-ion collider. So every aspect, I will leave you with a problem that is not expected to be solved as a homework, but a homework for you for next 10 years. So that the first data comes in into 2032, that's when we'll start solving some of those problems. But my aim is to elucidate them in the first lecture, and then we will all together project what can be done, what could be done in the electron-ion collider for the second lecture. Okay, so that's how it's going to be. So bear with me if I don't answer all the questions in the first one. Some of them will be in the second lecture, yeah, and some of them nobody knows, yeah. So that's how it is going to be. You already saw this nice knowledge of our understanding of the standard model. We have 6 types of quarks. Each one of them has an anti-quark. Each one of them has a color, 3 colors, as you saw in the introductory lectures by Marco. Then there's a lepton sector with neutrinos and charged leptons, and this is the column of bosons, and there were different types of bosons. Our aim is to focus on the glue this time. The problem with the standard model of what we know is that most of these are not detectable, or they are very unstable. So as experimentally, when we actually explore, we have very few stable means to measure them. And in this case, electron doesn't decay. I use electrons, easy to use them because they don't destroy themselves. And photon doesn't decay on its own, yes? It can convert into something else, but that's what. So normally, in the end of the experimental technique, you will always find electrons and photons play a very prominent role. We can use other things too, and we do, muon beams, for example. But to use them is more difficult and we have to use some certain tricks to get there. Anyhow, this is the history, this is the problem, and what we are going to focus here is the glue. Now you got that introduction in Marco's talk, that the difference, the fundamental difference between QED and QCD is the fact that the charge, the photon, is chargeless, it doesn't carry any electric charge, whereas the gluon carries the color charge, and that allows it to self-interact. That self-interaction is at the heart of all the richness and complications that we see in QCD. And this aspect will come again and again, and it has come indirectly in the discussion so far that you cannot calculate things unless you have to measure this, parton distribution functions. You cannot calculate them. Why? Because there is color interactions which are complicated. Calculations becomes difficult. Eventually we'll solve them with lattice QCD and such means that you probably have heard, but eventually we'll solve them. For now, we need to understand it better. Both are massless, by the way. Both are massless, zero mass. Remember that. That's another thing that I will come to in certain places. Now, so I've said this. The first hour is about EIC. Why do we need it? On the historical point of view, the science drivers, past experiments and the limitations. And the second one will be more directly towards, okay, how do we solve those problems that we couldn't do in the first lecture? So let me just jump into the inelastic scattering. And I always like to give you this example, just to make it very clear. The definitions were very nicely presented today. And here is my interpretation of it. If you wanted to understand the internal structure of a watermelon, you could do this experiment where you can take the watermelons at high energy and collide them. And what you would get is this. And you will answer a question, a fundamental question. What is the watermelon made up of? That's the meat, the seeds, and the cover that it has. But if I ask you a question, how were the seeds oriented, distributed in X, Y, Z inside the watermelon before you cut them? You will not be able to definitively answer that question here. And for that, you need a different type of collision. You need a knife to collide with the watermelon. That means you can cut it the way you want in whatever orientation you want. And now you can distribute. Now you can tell me, after this experiment, how the seeds were oriented, how they were distributed. Yes, it's a controlled experiment. The reason why it works is because, as Ravindran told you, the electron is a point particle. As far as we know, there is no structure to it. So when you have a collision between a structured and a structureless object, everything that comes out has to be blamed on the structure of the hadron. In this case, the watermelon. Yes. So that is deep inelastic scattering. It brings control and precision to the collision. And through the formula that we're going to show you now, some of you already saw in either of the two talks, I'll go a little bit deeper into how experimentally we look at that. So here is the deep inelastic scattering. You know this diagram very well by now. That's the virtual photon that is being exchanged between the incoming electron and the scattered electron. There is a scattered energy and a scattered angle. And here is the proton or a nucleus and whatever mess that came out of the collision. Yes, you heard very nice elucidation of how these things work and how we interpret Yorkein's scaling, et cetera, in the morning. So now I'm going to put them as an experimentally. What do I know in this? I know the incoming electron's energy and angle very precisely because I get it from the accelerator physicist in the experiment. I build the detector to measure the scattered angle and the scattered energy very well. That's a question of the technology and money that I have. How well I build an electromagnetic calorimeter. Then that means the difference between them tells me precisely the Q squared, the momentum exchange by the electron with the proton. And that is given by that. Yes? And that's obvious because the momentum of the electron has changed. And so you can write the 4 momentum and then simplify it as a function of only the incoming electron energy, the outgoing electron energy, and the outgoing angle. All 3 are known very precisely. One experimentally and one from the accelerator. Now I go to the variable y, which I call the inelasticity measure of that, PQ by PK, which was also mentioned in the previous talk. And if you solve it for what it really means, miraculously it comes out to be also a function of E prime, E, and theta prime. Then you go to the value of x Bjorkane in the infinite momentum frame, where it says the fraction of the momentum carried by that quark of the total proton momentum. And you take the ratio q squared by 2pq, that comes out to be q squared by sy, where y is that, q squared is that, and s is 4 times the total energy of the hadron times the electron. That is also very well known, right? In the fixed target experiment, the hadron energy is 1, it's sitting there. In the collider, it has some energy. Electron beam is energy. So that is also known very precisely. But what I want you to understand and keep in mind, that by just measuring the incoming electrons' energy, outgoing electrons' energy and angle, I have told you everything that happens in deep inelastic scattering. I know exactly how much energy was taken by the quark. Yes? Precision and control comes out because we know the incoming electrons' beam energy and angle very well. When you had a proton-proton collision, normally you take one proton to be considered in your mind as a target, and the other proton is the probe. But really the probe is inside that proton. It can be the quark or it can be the gluon. You don't know. But you can never know the distribution, the energy, and the angle at which that probe is coming. You know approximately what it is, and you have to deduce it from final states, but you can never know that beforehand. And this is why deep inelastic scattering, in my opinion, and I hope I can convince you eventually, it's a very precise tool to see the internal structure of the proton. Now, you can make different kinds of measurements. It was also alluded to in the previous talk. You ignore what happens here, and that's called the inclusive event, inclusive deep inelastic scattering event, which I just described to you. Only the scattered electron is measured. But you can be more ambitious. You say, what type of quark that was? For that, you need to know what happened to the quark after you hit it. Typically, when the quark comes out of the proton, it has to pick up an antiquark. You know that quarks don't exist in isolation. They have to pick up an isoquark and form a pion, kaon, or whatever else. That, as an experimentalist, I measure in the detector and identify it. Is it a pion, kaon, whatever? Once I know that, I know which quark might have been present. If it is a pion, you know it has to be UD bar or U bar D. If it is a kaon, it is US bar or S bar U. Yes? So from there, you can figure out what the flavor was. And one of the things that we will discuss in this school as we go forward and in the talks later is semi-inclusive deep inelastic scattering, which means that you identify the quark which was hit. And that is called here, and then from here you can do that. And then at one point you say you become so ambitious, and now we are at that point for the future electron-ion collider. We'll not only measure what comes out because the photon hit that quark, but what was the remnant? What was the target remnant? Yeah? So that's another thing that we want to measure in the future, because we understand now there is physics there too. We always knew it, but we didn't know how to measure it. In the fixed target experiments of the past, typically the target was a solid state target. Now imagine an electron beam or a muon beam coming and hitting it with large energy. It pushes the electron out or muon out, that we could measure. Most often we could also measure what was hit because of the angle with which the photon would push that particle out. But what happened to the target fragment was never known because it remained in the solid state target. There was no way to measure it. Yes? Unless you went to a gaseous target and you get some chance. But often, even the angle with which that comes out is a very restricted angle and you couldn't measure it. So if you want to go future, that future needs to have definitions and design of the interaction region so that not only can measure the scattered angle of the lepton, the quark that was hit, but also the target fragment that remained. That's our future aim. Now, sometimes the angle of that lepton is so small that you may not be able to measure it because it's too close to the beam pipe. As the beam comes in, hits it, and the angle is scattering, right? Sometimes the angle remains so small that you won't be able to measure it. What would you do then? Because you know the incoming angle, you can rely on the hadronic final state instead of measuring this. You still have additional variables, and you can reconstruct the whole kinematic event based on what you see here. Yes? So you have more than 2 or 3 variables with which you can reconstruct the event and check the correspondence between them. Yeah? So that's one thing. And then there is another one, which is something that we have not discussed so far, but I will discuss it and I'll use it later in the second half. The one in which the proton remains intact. So the proton doesn't break. One of the things we want to understand about inside the proton is that how are these quarks and gluons possibly moving? Intuitively, to think about it, we know that they can't be stationary. There has to be some kinematic energy there. If they have kinetic energy, and we know the proton is a bound object of a spherical size or fixed size, there has to be a quark moving in one direction and then moving back. Naturally, you intuitively see that there should be an angular momentum to it. There should be a transverse momentum to it, and we are measuring them, transverse momentum distributions. Some of you are experts in that already. Some of you are looking at generalized parton distribution functions, which then are related to the transverse motion in a more three-dimensional way, including the position, and leads to orbital motion. If you want to measure all of those, you can't break the proton when you are probing inside, because the fact that you break the proton is going to destroy that orbital motion. Yes? So we want to measure something called deeply virtual Compton scattering. The proton doesn't get destroyed, but here's an example where the photon comes through, interacts with the quark, excites the quark, that de-excites, gives a photon, and the quark sits back into the proton. And here, we have to measure the scattered proton to confirm that I did not destroy the proton. So in the final state, it is EP goes to E prime, P prime, or A prime, plus either photon, or in this case, there could be Jape size, et cetera, and I'll come back to that. And in case it is Jape size, then this track is not a quark, it's a gluon. So that's how we measure the internal dynamics that way. But this is another place where, again, the value of knowing the initial electron energy and the final electron energy is extremely valuable. Kinematically reconstructed event absolutely needs that. So that's the power of deep inelastic scattering experimentally, why we like to see precision and control. Yes? Here's a full list of them. You can go check them against each other. Just a list for you. You saw this formula this morning, the cross-section formula for any nucleus that goes out, and then there was F2 structure function, but there's also something called FL, the longitudinal structure function, which includes information about the gluon. And I think it will come back later in the discussion, but that's something that we want to, you will see. And then the total cross sections can be also rewritten like that way. And when we want to measure things, we start measuring the structure function, which is the momentum distribution of a particular quark type inside the proton. Yes, those are those parton distributions that you have been familiar with. But this is something that we will try to measure. So let me simply jump to the early experiments and fixed target. We'll see the lessons heard from the past collider. Everyone knows that we have done this fixed target experiments for about 40 years, from 1960, that then allowed us to discover the quarks at SLAC, and then all the way to about, even now we do muon scattering experiments at CERN. Yeah? But in between there was a Hera collider. Now if you remember that center of mass energy square S is equal to 4 EP, you can now see in the fixed target experiments with electron or muon beams up to 240 GeV or electron beams from this range, you can calculate the center of mass energy. And you'll see that they are range from 1 to about 25, 29, something like this. But once you put a beam in a collider with the 820 GeV proton beam coming from one side and a 27 GeV electron coming from the other side, you suddenly jump to 300. That's a large center of mass energy. Yeah? That's the advantage of of a collider, 27 is not so different than what we used in the past, because the electrons radiate all the time. So it's very difficult to effectively accelerate electron to very high energy, because it's low mass, it will radiate all the time. For muon, that is a little for difficult, simpler problem. That's why we could go to 240 GeV. Yeah, but the result is that the center of mass energies are very small. If the center of mass energy is small, your range with which you can measure inside the proton, if you look at the previous formulae, you will see that there's a fixed range in X, fixed range in Y. This you can explore. Yeah. So depending upon which part of the proton, in terms of X range that you want to measure, you either go to fixed target experiment or you go to a collider. So let me just jump you to the collider, assuming that we have done fixed target in the past 50 years. So this is a picture that you saw in another talk as well. There were two experiments, H1 and Zeus, with 27 GeV electrons here. And they were exploring, as I mentioned to you, this is X on the X-axis, X Burkane, and there's the Q squared on the Y-axis. The fixed target experiments sit all here. Yes, this is the fixed target regime. So you can, this simply comes from the same formula that we have been using so far. The Hera range is given right here. Because it can go to higher center of mass energy, then you can get to higher Q squared. S center of mass energy square is right here. The center of mass energy being large means that you can go to a wider range in X and wider range in Q squared. And in the lower side, so you want to measure it at the low X, you can go here. Yeah. So that's the general dynamics, and we'll do some kinematics in the second lecture to see what happens when you change the center of mass energy. That will be a homework for you a little later. What they measured was the F2 structure function at different values of Q squared. So you could measure F2 structure function here, F2 structure function here, F2 structure function here. I mentioned to you, this is the Q squared. What is Q squared? It's the resolution of your probe. Yes? Remember that? Q squared was the resolution. The larger the Q squared, the smaller the wavelength with which you're measuring things, right? Smaller the wavelength. Larger the Q squared, it's lambda equal to h bar times 1 over p, correct? Remember that? The p becoming large, the Q, that means lambda is small. That means you're probing the quark or the proton with smaller and smaller wavelength. Everyone with me? Yes. So that's what is going on as you go up here. That's the value of going high in Q squared. I'll show you a simulation later how that works exactly. Okay? So here is a measurement at Q squared of 15 GeV squared, and here is a measurement of the same quarks at 30 GeV. What has changed? Resolution has changed. But amazingly enough, what we saw was that the F2 structure function was looking like this at 15, started looking like that. And Ravindran told you today that there is a scaling that should be the same. So what is different about them? This was the hint of scaling violation. And that is because the quarks at different scales are radiating differently. They're gluons inside. The gluons are in action there. So that evolution that you see for the same values of X but different values of Q squared, different values of F2, that means that the F2 changes as a function of Q squared. And that rate of change of F2 will be defined. You will see, I'm going to show you, but I think you will see it in the more rigorously in the later talk by Ravindran, that is called QCD evolution of F2. And that is where, so this is the same function, F2 structure function plotted at Q squared. And you see, this is the fixed target regime, what is shown here. And in that means, and the X regions are very high, X being 0.65, 0.18. This is the region where you see the scaling, Burkane scaling. It's all flat. But as soon as you go to lower values of X, 0.003, you start seeing slopes to F2. That means it is changing as a function of Q squared, which example I showed you before, and that is where we find the gluon. This is where gluon resides. And the slope of that, F2 by ln Q squared, is proportional to the gluon. Yeah, and that's how we calculate them. That's how we get them to do a best fit of all these data Global analysis, they call them often. You probably heard such a name. And of all these data, knowing the Q-squared evolution code or fundamental called Alterelli-Parisi or DGLAP, yeah, Dokshitzer et al., Gribau, Lipatow, Alterelli-Parisi equation that tells you how they should evolve. And from that evolution, we deduce how much is the gluon there. I want to point out that these are X again, and these are different value, the quark distribution functions, but this is the gluon distribution function with its uncertainty. But one feature is that to fit the gluon distribution on this same plot, the plotter had to scale it by a factor 20. What does that mean? It means that the gluon distribution is so dominant, it's huge. In fact, it looks like that if you take that 1/120th part out. And what is the reason for such things? It is fundamentally the fact that the gluon is a charged entity. It can radiate, it can interact with gluons again. Remember the color part. And that means this kind of a gluon, this is simply gluon number on the y-axis here. So the fact that the gluon number increases as you go to lower and lower values of X, a simple interpretation of this is that the gluon splits into two. Those two will split into 4, 4 will go to 8, 8 will go to 16. This keeps on going until when you run out of total energy. Energy is conserved, momentum is conserved, nothing is being violated here. Every next generation of gluons will have a smaller momentum. And that is plotted on the x-axis, smaller momentum on the x-axis. So this is a very natural phenomena that we seem to see inside the proton. But the question then arises, what happens here? Does it keep on going infinitely up? It looks like it is. And as you know, physicists don't like infinities. There are no infinities. There should be a simple reason why that should not happen. But we have not seen it. We have not experienced it. This is something that we will leave for now and come back later. Here is a simulation of what we have so far, knowledge of the proton. What you see is a Parton distribution function, Q squared of 1 GeV. The resolution is not very large. Resolution in this picture is the size of this square, and this plot tells you which X region it is being shown. This is used using realistic knowledge of our PDFs. You go here, it still looks not so great, right? Nothing big. But now, we're going to change the Q squared. The resolution is going to change to 200 GeV squared. That means I'm going to now have a high resolution. And now I scan it again. Same thing, now you see the features that we are all familiar with, or people, if you've seen this. There's a lot of glue there. There are no quarks, the quarks are not dominant in the low X, but now you make that observable. The x-axis here, now these valence quarks become a lot more dominant. You can start seeing them. Yeah? So that's the way you should. But if I ask you, this is our current knowledge based on these PDFs, et cetera, et cetera. But if I ask you, how does spin work in this place? We don't have a definitive answer to it. So at 10 years from now or 15 years from now, I'd like to really make that realistic simulation like this, in which we will be doing all these kind of things. How are they moving in orbital direction? How are they moving in transverse direction? Yeah? So this is something that is the aim of the future. We'll come back to all of this later. Let me switch gears to that spin part that I just mentioned. And here I'm going to show you a clip of an experiment I did, nothing to do with QCD. The point I want to make is the following. Spin brings in very interesting aspects to life. We understand gravity, we understand electromagnetism, and I'm going to show you that if you understand, even if you understand those things very, very well, when you put those things together with spin, it's quite often difficult to explain, or it brings in a flavor that you really need deep understanding of that mechanics. So here is an experiment in my office. So there is gravity in my office. This black box has some magnets. There is a glass top, and I'm going to spin a plastic top, hand-blown top, with a little bit of a metal rim to it. And you see what happens, and hopefully you'll get the point that I'm trying to make. Here is the Here's the spinning. Here is the top. It's a plastic top, I'm telling you. It has a small metal rim around it. There is magnetic field here. You have to figure out what orientation of the field it is. It's homework after midnight tonight. So I'm not, there is no magic here. It spins. As long as it spins, it levitates. And when there's friction with the air, so it's slowing down. And at some point, fast, come on. I'm running out of time for my talk. Yeah, so it fell. So there's proof that I have gravity in my office, right? Right? There's for sure. So think about this. But it's not obvious. The point I want to make is spin always brings interesting things in our day life, right? There's deep understanding that is needed once spin is there. But it's not so different in QCD as well. And the next experiment we did will demonstrate that. So Elliott Leader and James Bjorkane you heard named in the previous lecture. They are two very senior theorists, and these are some quotes from them. In the 1960s and 70s, people were discovering new particles, hadrons, and they were scattering off of each other and come up with theories about what they might be and how they might behave and how QCD might evolve. We didn't know QCD at that time, but strong interactions. And then somebody would come and say, oh, if you think you know the theory, let's put spin on it. So now you polarize, you control the spin and do the experiment. If your theory is correct, you should simply be able to add spin to your calculations and predict what comes out. And most often than not, all these theories were destroyed. And that was the frustration that was summarized by these two great people in their jokingly, not seriously, jokingly. Just want to make sure. So the example I'm going to give you is the spin crisis. We know that the proton spin is half. And at that time in the 70s and 80s, we thought that the proton spin would come from the simply alignment of the quarks, essentially all of it. In fact, it was alluded to in one of your talk yesterday, that the alignment of the three quarks, this way, that way, and that way, should simply be resulting in the effective spin of the proton. And it was a very reasonable assumption, not knowing anything else. We didn't know much about glue at all at that time. And many of the other properties of the proton were calculable using that model. So people were very happy with it. Then came experimentalists like Vernon Hughes. What he did was he put spin to that deep inelastic scattering. So all the formula that we just talked about, now we only have to add spin. So now we have a lepton which has a spin, and hits a target which has a spin, and then there is a spin plane, there is a scattering plane, and you repeat those calculations for cross sections with the spin in it, what you saw in the morning. Simply you do that measurement again, but now in this example, I'm doing two kinds of experiments. I'm making the electron spin this way and the proton spin this way, and then comparing that cross section with the electron spinning that way and the proton spinning that way. So it's just simply hitting the difference in the cross sections when spin is involved. Before this, we ignored the spin, now we are going to involve it. And that's what those cross sections look like. And the experiments were carried out at CERN and at SLAC to do this kind of a measurement. So this anti-parallel cross section minus the parallel spin cross section, the difference between them is easier to measure rather than to make measurements totally independently and making the difference between them. And I'll come back to this point as to why that is important too. The lepton-nucleon cross-section which is orthogonal, instead of making cross-section, it's prudent to make measurements of the differences. Asymmetries of many measurements might cancel, and you can get double longitudinal spin asymmetries where this is the difference and this is the average of the two, okay? And this is a similar thing for transverse spins. You take one of them to be transverse and you move the spin this way versus that way. And then you can start calculating things for the asymmetries and you get a simple formula that looks like this. There's no difference. This is a physical cross-section difference between when the spin element was against each other or when there was with each other. And then you can get some structure functions, which are spin structure functions. You have not heard them, but you will hear them soon, hopefully, where instead of F1 and F2, you have G1 and G2. There are nothing major other than now we have looked at the spin. Yeah? Now, why did people do that? People did that because, as you heard in the previous lecture, the quark contribution. So the photon comes in and hits a quark or an anti-quark. The photon doesn't know the difference between quarks and anti-quarks, right? It doesn't know. And what this experiment tries to do is to say how much of the quark anti-quark of a particular flavor is aligned with the proton spin. That question you can ask. You cannot ask the difference between them, but you can ask the total. So when I say delta Q here, it's the difference, it's the sum of quarks and anti-quarks. Okay? When I look at the photon, I don't see how I can make a difference. If I had used the W instead, weak interaction, remember? Photon, W is just the heavy brother of the photon, right? In that standard model. If you have a W plus or W minus, then you can see the difference between U and U bar and D and D bar. Yes? Flavor and anti-flavor. Yeah, we can, photon we cannot. So in these formulae, I cannot distinguish yet. Yeah, eventually we will, but not yet. The sum of this is the G1 spin structure function is held summed over all flavors of E squared, the charge square, and the difference between the quarks aligned with the proton, anti-quarks aligned with the proton, quarks anti-aligned with the particular flavor. And that's how we write this down. And the first movement of this is the total spin carried by that flavor. Yes? For each of the U, D, S, you will get this part. Now, if you take the full momentum integral, it comes out to be this. Take my word for it, but this is what comes out. 4 by 9 by delta U, 1 by 9 by this, 1 by 9 by this. You can see that 1 over charge square is coming out there. Yes? 4 by 9 is just 2/3. U quark is 2/3 square of that. D is minus 1/3 square of that. And then if you write this slightly differently, people realize that you can see delta U minus delta D is what we call A3, is a constant, comes out to be. And then this one, it comes out to be A8, which we can measure. These two we can measure from neutron decay and a hyperon decay. Experimentalists, we knew how to measure them. We had measured them. So that what remains is amazingly a beautiful expression for delta U, delta D by delta and delta S. Which means that the sum of the spin carried by U, D, and S quark, if S quark is there in the proton, maybe a small amount, then you could interpret this last function, last part, as the total quark's contribution to the proton spin. So if you know this, if you know that, and if you measure this experimentally, then you can know what delta sigma is, which is the total quark carried by, the total spin carried by the quarks. That was the logic, yes? And then there was, so this was known, but we didn't know at that time we can measure these things precisely enough, experimentally. And then came two bright scientists called Ellis and Jaffe, John Ellis and Robert Jaffe, in their summer program at SLAC in 1976 or so. They came up with a simple concept. They said, hey, we know these, we know that, and what is the value of S quark in the proton? Let's assume it is 0. It's small, it's going to be small, so let's get rid of that. And then suddenly they said, now we can calculate how much, what you should expect. Now, if you give such a challenge to experimentalists, they say, okay, cleanly measure the structure function of the proton, take its integral over all values of x, and Marco, or at that time Ellis and Jaffe, theorists were telling me, this is what you should see. The clean challenge to the theory, either it is yes or no. Yeah? And that was how it was measured first, and people saw consistency. At SLAC, it was on consistency. No problem with that measurement. But simultaneously, there was an experiment going on at CERN. With a muon beam, with a much larger muon beam energy, that means it could go to lower values of x, higher values of s, lower values of x. And then we started seeing problems. So at low x with polarized spin, we saw problems that allowed us to see these measurements. So the experiment was simply this. You took the proton, you aligned it this way, and then you have these two U quarks aligning this way. Your model is that the spin is carried by quarks in this picture, right? Keep that in mind. Now I'm going to do a Gedanken experiment here to explain what was going on. And then it was scattered by this one spin one photon from the electron that came through or muon that came through. Now, the interpretation in my model here is that U quark always has a spin half, correct? It always has spin half. You can never get a U quark with spin 3 halves. Yes? So my simple interpretation in the model is that when you have a spin 1 particle hitting a spin half particle, it flips. So that kind of interaction is possible. But if I hit the quark which was already spinning in that direction, then the total spin is 3 by 2, which is not physical. The quark spin is not 3 5. So in my Gedanken experiment, that's not going to happen. Yes, it's just a wasted interaction. So here is what that Gedanken experiment is. So here there are 2 quarks that can flip. So out of my 100 or 1,000 billion tries, 2/3 of the time you can flip. Then I use my magnet to turn the magnetic field the other direction, and the proton now spins the other way. If the proton is spinning that way, and the spin is coming from the quarks, then the quarks also should move. I didn't actively move them, but that's the rule. So now we have 2 quarks moving that way, or spinning that way, and U1 moving that way. And suddenly the probability is 1/3. So now, if that assumption that the quarks carry all the spin is correct, then the difference between those two, I know it's 2/3 minus 1/3 divided by the sum. Precisely known. That's why people could calculate what would be the total spin of the quarks. That was the idea behind the Ellis-Jaffe. Yeah? They blamed it on UND and said, this is what you should expect. To get there, we have to get into some experimental things. I promised you that I'll give you some constraints. So here is the target, and in one case it was moving that way. And the beam comes through which was spinning this way. And you have this anti-spin condition here. In this one, I have moved the target to the other side. So suppose I build the experiment and I make measurements on 30th of January. I go home, I'm tired in the evening. 31st of January, I come back. I move the detector such that now the spin is moving the other way around, and I make the same measurements on the other side. And then I say, okay, let's see the difference. Is that going to work? Is that going to be enough? You said yes. But I say, I am questioning that. Today, humidity might be different than yesterday. Yes? Today, my detector might be working slightly differently than yesterday. So the differences that come out of the fact that I came on day 1 and compared the data with day 2 is not possible, is not allowable as an experimentalist. So what do I have to do? I have to create exactly identical situations when I do this and that. The best way to do this is to move the spin as often as I can. Rotate them and compare data sets very quickly in time so that the beam flux is the same, the target size of course remains the same, the detector size is the same, detector efficiency also remains the same. So experimentally, we have to worry about that aspect first, because that's the physical, the false asymmetry we want to avoid. Or we cannot never avoid it, we have to suppress it as much as possible. So if I know that the asymmetries I'm going to measure are of the order of 0.1, difference between them, I want to go 100 times smaller when I make a false asymmetry. Yeah, that's the aim that we keep. Not always succeed, but that's the aim we keep. They have to be small 100 times. So here is that measured asymmetry. When these are anti-parallel, this is parallel, you take the sum, and then you can calculate this explicitly. Number of particles in the beam, number of particles in the target, you know, the events. In the cross-section, this is the physics one, physics cross-section, detector acceptance and detector efficiencies. If I can keep all of them exactly the same, then the A measure is simply this. But as I said to you, this can never happen. We just have to measure and suppress these differences as much as we can. So that's why we made these tricks. We say, we put those 2 targets together. So the muon beam or the electron beam can pass through both orientations simultaneously. Yes? Now I don't have that argument. On 30th of, by second, I know the same detector. However, there is a small difference. This target has a different angle subtended with the detector compared to that. So there is a small difference in the acceptance, the opening angle, cone. How do we get rid of that? Well, I switch between polarizations of this and that once in a while, every 6 hours, every 4 hours. I flip them so that this orientation comes here, that orientation comes there, and then you try to reduce that again. Yes? So we try to come up with the tricks like this all the time. But remember this, in the fixed target experiments, this motion would take 6 hours. Sorry, we would do it every 6 to 8 hours because the motion from here to there would take about 20 minutes to half an hour. So that was my dead time. I couldn't take data. But that was the best we could do at that time. I will bring this point again a little later, so remember this point. So this is what we had. The experiments were done at 4 different places, at DAISY, at Jefferson Lab, at CERN, and at SLAC. And I'm going to show you the early results from SLAC and CERN experiments. Here is what I said to you. When the beam energy was low, center of energy was small, you're at high X, and you saw no difference between the theoretical expectation and the asymmetries that were mentioned. But as soon as you went to higher beam energy at SLAC, at CERN, you saw that there was a systematic difference in the asymmetries. And you calculate the G1 spin structure function from there. This is what Ellis Jaffrey was estimating, assuming they're reasonable, making their reasonable assumptions, but this is what the data showed. Yeah? In fact, if you look at the data, the uncertainty was so large in the extrapolation and the total integral that first of all, it said there is no correlation at all, which was a shock. It was called the spin crisis by some of these senior physicists and became big news at that time. It was called the crisis for the proton spin structure. So eventually we reduced the uncertainty to a smaller number, so it's not 0, it's about 15%, I'll show you, or 20%. But this was how we saw something new, and now we learned something new about the proton structure. Yeah?
Thanks. If delta sigma is the fraction of nucleon spin carried by the quark, so the probability, okay, then this slash over 2 is wrong in the sense that delta sigma cannot be larger than 1.
You're right. Yeah. So I think I have a problem with the factor 2. Yes, it should be simply delta 2.
So please erase in your mind, erase this slash divided by 2.
I found one more typographical error later, or actually previously, I have missed it, but okay, that's fine. Thank you. We'll have to fix that. So the consequence was that we learned that eventually that with much better accuracy, again, this is a half this, that this is small. The error bar has been reduced from 0.17 to 0.03, but the message we have learned is the quarks don't carry all the spin. The gluons have to be part of it. And now we are even better. The gluons, and I'll show you what was done. At that time, we were expecting extremely large values of gluon carrier because people were not coming in pictures with the orbital motion, and that contribution was not completely in the picture. And the global fits that were done for spin structure function were giving very large values of delta G. And that's shown in the 1990s snapshot. So you needed a better program, better look at the gluon distribution, and that led to the proposals for the RIC spin program. And I'll show you a bite of that before we jump to the EIC. So here is what we have learned. Here is my gluon region, low X, high Q squared, low X. And then this is what we got from such an analysis. Now you could ask, you could do the same analysis with the G1 spin structure function. You could look for scaling violations of G1. Yes, because that's the same physics. I could look at the slope as a function of Q squared. And we did, we tried to do that. And here is the comparison. So here is the same data I just showed you for F2. Here are the fixed target experiments. This is the collider experiment. The HERA data came here. This is where we want to go. And then we compiled the data at that time. This is a figure from 1998. And here is the fixed target experiments for G1. And you see this red line here. Kinematically, it is the same line as that because we only had fixed target experiments, which means that we were in the spin physics. We had never explored the region. We couldn't explore the region where gluon dominates the inside of the proton. So you couldn't see the slopes. Yes? And what do you need to do that? You need a collider. So this was where, at least I started thinking that we need a collider for EP, polarized collider. This is the beginning of that concept that I wanted to present as an electron-ion collider. This has happened. This is a much later slide, about 2009 or so, or 2007. Again, since we have no collider, we have much better understanding of this data set, but nothing that gives us the slopes. Yeah? And that became a remaining part which keeps on coming to us, that we need a polarized electron-proton collider. The low X extrapolations without data are showing us what happens to G1 structure functions in the low X. You can see that there are no data here, which is where you really want to go and make measurements. Yeah? And that's the limitation that we want to go over. So now our summary, again, I have this factor 2. I don't know how that, okay, so delta sigma should be just delta sigma here. You can see that the 80s, we came to know that. Now we know that the RIC has, the gluons play a major role. And now I'm going to show you a snapshot in the future that we also now know that that also will not explain. You will have to have some good understanding of the transverse dimension, transverse motion, and the orbital motion. That's how the story grew. And we are now more mature in understanding that that delta sigma, delta G, which is the gluon's contribution, has to be measured. And then there is more orbital motion of the quarks and gluons. How you want to split it this way is something that we will be discussing in theory, but this is the biggest picture we are going to go after. So let me give you a precursor to the electron-ion collider before I stop for my first lecture. So here is what we did so far. We had electron scattering off of a photon, and then it interact with the inside of the proton. Yeah. Now, if you wanted to make measurements of the glue, we already knew by this time that from HERA that at high energy, protons are full of gluons. So if we polarize the proton at high energy, which was technology that just had developed around year 2000, we were going to use them at RIC. That's where we wanted to make measurements to look at the gluon spin. The concept is the same. We make measurements with this versus that all the time, and make measurements for the gluon's contribution to the nucleus. So here is the new collider. At that time, 2000, you had the polarized protons coming from here. Then you could put them into AGS, alternating gradient synchrotron. Then bunch by bunch, they would go into the blue and the yellow ring. And then they would go clockwise and anti-clockwise and collide at two different places with lots of effort to maintain the polarization as you accelerate them. It was a novel thing. Nobody had done that before at very high energy. We had to invent a new kind of a magnet called the Siberian snake magnet. We had to invent these spin rotator magnets and then have collisions of protons in this direction versus that direction in two different areas of Phoenix and star. I will not give enough credit, enough weight to this part because I want to jump over. But in the discussion part, I'm happy to go in details. And I think Sanghwa might go into the details in her talk and her lectures in great details of this. But these are the kind of magnets that I mentioned to you, the Siberian snake magnets, and why they are called Siberian snake, etc., will come in discussion part. So I want to emphasize again, remember the changes in the polarization spin? Every 6 hours, 20 minutes I would lose, etc., etc. Now in the RIC, we have to fill the beams with two different spin orientations. So as we come into the RIC, you either fill the ring with this orientation of the proton, transversely vertical up, or this. So bunch by bunch, we could control that. Every bunch comes in at 100 nanoseconds. And then the other ring we could fill separately with our own, whatever I wanted the pattern to. And in this picture, it shows that one of them is giving plus, minus, plus, minus, plus, minus. The other is plus, plus, minus, minus, minus. So now what happens? This plus comes in and that plus comes in and collides at this location. So now we have this orientation collision happening. 96 seconds later, there is a minus one that comes with a plus. So now I have flipped one of them. Yes? 96 nanoseconds. Third, plus, minus, minus, minus. So now I have this, I have that, I have that, and I have that. I think it's reasonable to assume that my detector is going to be the same over those 96 times 4 nanoseconds. Yes? So those false asymmetries that I worried about are gone, essentially. Yes? We couldn't believe it to start with, but we measured the first false asymmetries that came through were at the level of 10 to the minus 3, 10 to the minus 4. And maybe Sangwa will talk about, she was part of that tremendous calculation at that time, the success of the program. Oh, that's the source. So we take the way we fill the ring, we use the laser with a certain orientation and the other orientation. There is no other way. Atomic, yeah. And we can measure them. We can measure the orientations in the collisions. That's also part of the measurement. So what we call local polarization. In fact, we know now, we didn't know it, we discovered it in 2000. That's a discovery story. I can talk about it in the discussion part. But before Rick came along, this was not known. We couldn't really say that. And we challenged it, and we figured out a new way to actually know this. Now we know this to a value of about 1 degree, the precision. We know exactly how to calibrate that. So those were the 2 experiments, and I'm going to take a few more minutes just to finish this part. We made measurements. This is the gluon distribution, as we knew it. You see, there is a large uncertainty. Spin, polarized gluon distribution. Be careful, not this gluon. It's polarized gluon distribution plotted as a function of x, and you saw that there are uncertainties in it that range much, much more significant. Right? And we made measurements here to bring it down. If we make the measurements there to bring it down, there is still some uncertainty here that continues. You see that those 3 lines continue, but we did much better than what fixed target experiments had given us. So from here to there and from here to there is the improvement we got because we constrained it in the middle. But this is irrecoverable. And that is shown here. I think Marco showed this plot in his presentation. This is where we were in our global understanding of the gluon uncertainty. Once you compare on the x-axis the high X gluon's contribution, and this is the low X gluon contribution. So you can see how large the low X gluon contribution uncertainty is. And then suddenly after Rick, we measured this here, the uncertainty in this direction goes down, but because we have not really pulled down this part, which is the location where the electron-ion collider will make measurements, you still have a large uncertainty in the low X part. Yeah? So that is the sort of the motivation. Let me skip this part, and then I want to make one point before I go, because this is important for the transverse momentum discussion. Here is something that was known or assumed for a long time. And this is a lesson in historic mistakes, in my opinion. And I'll tell you why. So we have transversely polarized proton hit in a proton, and a pion or a kaon is produced. And we had seen left-right asymmetries in these particle productions, either in identified or unidentified. We had seen that. But we're talking about 60s and 70s. QCD didn't exist. Hadron structures was barely known. So experimentalists or theorists didn't know how to interpret them. There was one group of experimentalists who was making these measurements continuously in those 20 years. But the entire community ignored it because they didn't know how to take care of this, incorporate that. So transverse spin physics got a lot of bad rep in the 80s and 90s because there were some experiments that were wrong, but mostly it was right, and people just ignored it, in my opinion. It took the Rick data to come in, and some of the semi-inclusive data from Hera, from Hermes experiment in the late 90s and early 2000s that really established that this is serious, we need to make measurements. Also, by that time, we knew that the quarks and the gluons were not fully explaining the spin, so the remaining part had to come out with some kind of transverse motion, transverse dimension, orbital motion. So that was also an indirect, right? But this was facing us. And that was because there was a paper by these very established physicists from 1978 that said the estimates of transverse spin were of the order of 0.01%. Very small asymmetries, yes? So it is difficult to sort of take that seriously and try to measure it because experimental tools were also bad. But anyway, this is something that was ignored, but here are the data from those times. I can show you this is from 76, this is from 2002, this is from 1991, and you can see that the ZGS experiment at facility at Argonne National Lab, Fermilab, they were measuring robust, very, very precise asymmetries for pi pluses, pi minuses, very systematically. It was not even random. It was very systematic, remained all over. And this was the first time the experiment at 62 GeV in center of mass was made. Before that said, oh, this must be soft physics. We don't understand that. We don't know how to deal with it. We'll ignore it. So all this was ignored until Rick came along and measured it, not only at 62 GeV, but also at 200 GeV, we saw those asymmetries. And now people said, at 200 GeV, there is no way this is a soft physics. There must be something a lot more than that. And I think that is where the whole thing started.
May a short comment? You see that you said correctly, not only unidentified pions, but also identified pions diverge. You see pi plus, pi minus, different. This means that any orbital motion of partons that produces this split, coupling to the polarization of the incoming proton, it must be also flavor dependent. Because the content, the quark content of the pi plus is different from the one of the pi minus.
Yes,
pi one plus, is up and down.
U d bar. Pi minus, U bar D.
Exactly.
So you're saying if you have pi pluses systematically showing positive asymmetry and U bar showing the other way, you know that D somehow is behaving very differently than you. Yes, in this picture.
This means that the up quark has a transverse momentum distribution which is different from the down quark. For example, from other flavors.
Right. So all those things started becoming obvious now that we have near it. And then the field began with people like him and Asmita. Now it has become a robust field for investigation of the proton. There were origins of this. There's something like the Collins effect or Collins-Heppelmann effect, where the direction of the hadron is carried by the initial momentum, the fragmentation here, or there could be some orbital motion that said, okay, you had actual motion and then you hit it at some point, and then the quark that starts coming out comes out at an angle because of its initial motion and the direction in which you got hit. So you can get two of them, and then were tricks to figure out how to reduce the uncertainty between them, how to solve them, et cetera, et cetera. And so there is a field that you will see as to what is the origin of all of that. Last but not the least, we also don't know much about the nucleus. And this is one slide on that. If you looked at this ratio of F2 structure function of the calcium to X2 function of the deuteron, and compare that, that's the ratio. Deuteron is more like a proton. That's like what we wanted to do, right? Deuteron is very close to a proton. So if you take the ratio of a nucleus to a proton, and you look at the F2 structure function, the fact that it is not 1 tells you that the distribution changes, and it changes as a function of X. This was a surprise also. And this, particularly this behavior, it starts going down at extremely high X, comes up, goes positive, and then goes down. What happens in the low X is completely unknown because nobody has ever measured it, even today. Yes, there are explanations for this part which will come up in various future discussions, but here there is nothing. Yeah, and we need to make measurements. If you want to make measurements at the low X with the nucleon, the only way you do this is put it in a collider. Yes, there are other things that will go interestingly in the collider, but this was one of the things that we want to measure. So these were the lessons learned. This is all, I will not say that again, we have gone some over the time. There is measurement of the glue, measurement of the orbital motion, transverse motion. We want to make measurements over broad XQ² range. We want polarized protons and electrons in the collision, and then officially look at low X behavior in nuclei. And all of that points to the fact that you need high energy, you need high intensity of the beams because you want to make precise measurements, and you need different types of nuclei, and better the beams be polarized. Yeah, that became the case. That became the case for the continuation into the second lecture. So that's it. And I'm happy to take questions now or during lunch.
Yeah,
or in the
Abhay,
evening.
actually lunch is at 1. Your second lecture is now.
Oh, right away?
Yeah.
Oh, perfect. Then I can take a few points now.
Abhay, may I make
Yes,
a
make.
further comment? Again, on the story of the fact that the data seem to suggest that the transverse momentum distribution of quarks is flavor dependent. So up, down, strange, whatever, have a different distribution. This has implications also on a much more important thing for the standard model, which is the determination of the extraction of the value of the W mass. Mm-hmm. You know that the most precise determination of the W mass is through electroweak processes, but there is also the strong processes. Proton-proton collisions producing W decays, and then you measure the transverse momentum distribution of the decays, and also of what is missing, because in the decays, in principle, there should be also neutrinos, okay, that you don't see in the detector. Now, if you study this transverse momentum distribution, what is missing in the current analysis is the information that the W is charged. So it contains a flavor asymmetric combination of partons, up anti-down for the W plus and down anti-up for the W minus, okay? And therefore, if you try to extract the value of the W mass, looking at the transverse momentum distribution of the decay products, you need to include the information that up and down quarks, anti-up and anti-down quarks have all in principle different transverse momentum distribution. And this is missing in the current analysis. Basically, the W plus or W minus are treated as a Z0, as they were a neutral particle made up of up, anti-up, and down, anti-down combinations. So flavor blind, in other words, which is not the case. So this outcome and these studies of transverse momentum distribution that will come up in next lectures are fundamental also to reanalyze the value of the W mass, because we are basically underestimating the total uncertainty on the value that is extracted from using strong interactions. And of course, this is important because the W mass is one of the most important parameters of the standard model, and we need to know it with very large precision. Otherwise, because this affects the study of things beyond the standard model. So to explore things beyond standard model, you need to know the standard model at a very precise level, because any difference that you see in the experiments can be correctly interpreted as something beyond that.
So he's talking about this part here. Yes, this is one of the standard model parameters. Weinberg angle also has a W, and the more precisely we measure using this in the future, UD, that has an impact. Yeah. Good. All right, let me just then, if I'm going to continue, that's perfect. Let me just continue. So now we will jump and tell you more about the EIC itself. What I've told you is a limited Q squared range, limited luminosity, limited Q squared range, limited polarization variables, limited nuclei, or no nuclei so far. Yeah. So now we'll start looking at the physics of that. So here is the same precision and control. I think this is for reinforcing what I was saying. You want to make measurements with inclusive to exclusive. And as you can probably imagine, now that you know also the concept of acceptance, remember the acceptance that we had for the detector in the cartoon? The cartoon showed you the scattered particles going into that detector. Now imagine you have a collider. Electron is coming from one side. The proton is coming from the other. The nucleus is coming from the other side. When they scatter, they go that way. They go that way. Depending upon what exactly happens, they will go from there. You can figure out what the kinematics of them is. But that means that if you really only want to make measurements of the scattered electron, you can have a fairly limited acceptance. Yeah, because the electron is coming very clearly from one side, predominantly is going to go that way. There will be events in middle, but it's not rare events. You could be saving money. But if you want to identify and measure the hadrons, which are now going in the other direction, you need more acceptance times luminosity. You need more acceptance. Yes? And for this part, you need all acceptance. You don't want to lose anything that goes even close to the beam pipe. That's the only way to measure it. But there is nothing realistic about it. You can do your best, but not all. Yes? Then you have to do some extrapolation, but it needs to be minimal of your acceptance. Yeah? So that's why I didn't emphasize so far, but low luminosity is this region, acceptance increases as you want to go from inclusive to that. It's always the product of them, remember that. It's always the product of acceptance and luminosity. You can have a huge luminosity, but no detector, there is no acceptance, right? Think about the extreme cases. Huge luminosity, no acceptance, or you have a full detector and you have one electron hitting every 2 years. No physics, right? So think about this way. You need the product. Now, here's the example that you can actually calculate yourself and try it for a few numbers. What I've shown you so far, the xq squared plane, I want you to calculate, knowing this, the values of x and q squared at different values of s, center of mass energy. Because one of the features of the electron-ion collider will be that we will be able to collide at different centers of mass energy. Yeah? So if you want to focus on the high x and low q squared, I'll run something to measure this part very well. Then when I want to go to the low x part, which is the original reason why we wanted to go, we want to increase the value of s right there, and we go in that direction. Yeah? And that means you will be able to measure in this region here, including the low x. The answer that you will see should look like that. This is a simulation I'm already telling you, 5 on 50, 10 on 100, and 20 on 250. You see how the corner gets filled with the lowest energy, intermediate energy, and the highest energy. You start seeing a hole here, which was smaller here. Yes? So I want you to look at these slides, pick a value here, and see if you can actually calculate all four. X, take Y, and you know S. See if you can figure out the entire kinematics. Yeah? It is not just calculation, you have to think a little bit about it. But it's something that you can do in an Excel sheet. Yeah? And play with it. Then you can look at my formulae for where the jets go. Jet here is my interpretation of a quark. Yeah? Quark starts moving because I'm hitting it hard, it starts moving in some direction, it starts to come out. At high enough energy, it comes out with a lot of other particles along with it. A lot of friction, QCD friction with it. That's called a jet, a pencil-like hadron beam that emerges, or hadron bunch emerges from such a collision. So you can actually use those formulae in those first 3 slides that I mentioned, and you can figure out where does the quark go on the q squared versus x plane. And you'll see that the electron scatters here, the quark scatters that way. You can actually plot these, again, Excel sheets. You can figure them out. You can really calculate them. You have to be just careful, mindful about the 4 dimensions, basically. And similarly, for a different kinematic, that was for a 10 on 250 and 5 on 50. So if you can show one of these curves, that should be enough. You don't have to show all these plots, but calculate one of these curves, that is, and should look like what is shown in these slides. Here are multiple ways to reconstruct events. I mentioned to you because we will either measure the inclusive method or the hadron final state method, or if you're measuring electron angle and the hadron angle, you can measure that too. So there are 3 types of measurements like that: the electron method, the jet method, or the quark method, or the double angle method. They all give you the same information. I told you the system is over-constrained, and you can check one against the other. And at some point, in some regions of x and q squared, one of them will not work because you don't have good acceptance for a hadron in a particular regime of x and q squared, or you don't have good acceptance for the electron, and then you get into trouble, so you rely on the other one. Yeah? But here too, you have three ways to measure in any variable. So that's what these formulae are about. So now let's dip, with that knowledge of this, now dip into our physics again. So now on the x-axis, I have a parton density. It increases on the x-axis here. So this is 1 over x. And I've shown this schematically by showing at low x, we have a hadron. It looks like more valence quarks bound by gluons. And then as you go to lower and lower values of x, the number of gluons increases and the total parton density is increasing. So that's the x-axis. The y-axis is still the q squared. And I told you it's resolution. The higher the resolution, the precise measurements of pictures of the inside you are getting. And somewhere you go from non-perturbative to perturbative regime. Yeah, somewhere there's a transition happening. So the part where it is non-perturbative, you have a strong coupling alpha, and then you go into the weak coupling, where perturbative methods start becoming reliable. Yeah. So then you have many things that you probably have learned or will learn in this workshop coming through and the school coming through, and you will see that all of these words will be used somewhere. The electron-ion collider, as I said, precision and control. So on this plot, you should be able to go from one region to the other by tuning the machine and then selecting events with a certain characteristic. You should be able to move from one region to the other, yeah, in a controlled way and a precise way. And that's what the electron-ion collider will give you. Yeah. So the highest part is high resolution. That's weakly correlated. This is where something is well described in perturbative QCD. The hadron structure sits here. So nonlinear dynamics emerges as you go in that direction. That's the most difficult part, the non-perturbative part to calculate. Here are places where you can do systematic studies from going from one to the other. And then one of the things that we want to measure, remember that gluon density going up, infinitely going up? What does that mean? It means that you're going into a regime because that was calculated using perturbative QCD. Remember? That was a double next to leading order calculation. And now these days there are even higher order calculations. So perturbative QCD works there. Data are at high Q squared, high energy. And now we are going to low X, which is in this direction. So we are in the weak coupling regime and high parton density regime. And we haven't discussed that yet, neither in any of the class. Well, actually, he introduced it in the theory part. And that's where the gluon starts dominating. But you are still not in the non-perturbative regime, but a perturbative regime. If we are lucky enough to reach that in the collider regime somehow, we will make those measurements for the first time, very clearly, cleanly, and with control. That is the argument to go to highest energy of the electron-ion collider. And the argument there is that it will not have enough energy to probe this region with the proton, but I will use a nucleus. Nucleus gives me a larger number of partons collected together. And as was mentioned, like the proton at high energy, where it gets Lorentz contracted, the nucleus is also going to be Lorentz contracted. If I can sense that using the high energy probe coherently, the entire conglomerate of this high density nucleus, like a pancake, I'm going to enhance that gluon density as I see it. Yes, and there I will try to see if I see any evidence of something new emerging. So that's the picture, overall picture that we need. One of the things, consequences, and people think about this, talk about this, is that the proton mass puzzle. You look at the three quarks that make the proton, the UUD, and you ask, what is their collective mass? And we know the mass of the quarks, isolated quarks, and if you add the mass of the quarks themselves, comes out to be about 2 times 10 to the minus 26 grams. But we know the proton is 100 times that. Yeah, it's about 100 times that. And the only difference between that is that we know that they're bound together with the gluons. And the gluons binding them creates that extra energy that is needed to keep the proton intact. Remember, the gluon is massless. So you should be amazed at this beauty that nature gives us, that most of the mass in the universe, protons and neutrons, which make the entire visible universe, comes from a zero mass particle, the interactions of zero mass particles. Yeah. In fact, in that public lecture, I don't know, I call this a super God particle. because the origin of mass that is blamed on the Higgs boson only gives to 2% of the total mass of the universe. 98% is coming from something else, the glue that we want to study with the electron-ion collider. All right, so this is really important. This is the visible universe as we know it. So this is not just a small problem with a proton, it's the entire thing. So we made the case to a place called the National Science Academy for a future collider that said that we want a very high luminosity collider, particles passing through each other at this rate, 10 to the 33 to 34 centimeters square per second, which is about 100 to 1,000 times that of the Hera collider that I mentioned to you before. Then the momentum range, the center of mass energy range, somewhere between 20 and 100, upgradable if needed to 100 to 140 GeV. We want polarized beams. We need a large number of nuclei and up to 2 detectors. And that was blessed by this August committee, which is an external committee, just not us who want to make that experiment, but an external committee that said this should be built with these parameters, which were defined in the science case, the white paper we call it, that electron-ion. So the 3 parts on which we built our case was how are C quarks and gluons and their spins distributed in space and momentum inside the proton. Remember, now we have to go space and momentum because we have to go into 3-dimensional pictures. Not just the moment, just the alignment, but momentum distribution, position distribution, and all. Yeah? So that's what we need. How do the properties of the proton emerge from those interactions? That's something that we need to learn, we need to understand. Things that I've not mentioned so far, but will be part of the program, is that when you hit a quark inside a proton inside a nucleus, with a deep inelastic probe, how are the color interactions? What are the kind of interactions happen? When the quark here is light quark versus heavy quark or the flavor quark, separated by that. And what happens at this edge? When the quark tries to come out, picks up an anti-quark, gets neutralized, color neutralization. Yes, it's at the root of confinement. Why don't we see free quarks in the world? It's at the root of that problem. How does that happen? We need to systematically study it. We have lots of control. Because I told you, I want to study this as a function of energy of this, but also have another control. I can control the size of the nucleus. I can go from deuteron, which is the smallest nucleus other than proton, to all the way to uranium, which means that I can control this interaction length very precisely because I know the size of this nuclei, yes? So I can do experiments with that. That brings in additional control and flexibility for nuclear sciences. And last but not the least, I mentioned to you before, is that what happens to this gluon density? Does it saturate at high energy, or does it keep on going up? Now, intuitively, you know that this cannot be, right? Infinities are not possible. What could be the possibility? We are all confined inside the proton or the nucleus, and the gluon density keeps on going up. At some point, it's going to be so crowded that there's going to be a huge amount of glue around it, so the gluons can interact with each other to recombine. They just don't have to split into 2 and 2 into 4 and 4 into 8 and 8 into 16. They can also go in the reverse direction if you have enough of them. But that reverse process will only start when we reach that initial saturation state. Right? That's when the recombination and the opening will become equal, and then you'll have a saturated state. We have not seen it, but this is one of the aims of our collider, that we would like to see if we can reach it with the energies that we have. So, pictorially, here is what we have in the polarized. Now we are all familiar with these plots, right? X and Q squared. So X is on the X-axis here, Q squared is here. These are the fixed target experiments, and the electron-ion collider with different energies can measure regions here. And you can see in the X region, in the polarized protons, it gives you a factor of 2 orders of magnitude lower X, and for each X, it gives you a range in Q squared to study the precise evolution. Remember, we want to study G1 structure function as a function of Q squared to look at the slope of the G1 structure function, exactly as we did for that F2 structure function. And this will give us the first reason why we thought about a polarized collider will come out of this measurement very quickly. Yeah? Same thing for nuclei. These are the past experiments on fixed target with muons, and this is where EIC will sit and make significant measurements beyond what has been done. Here is a simulation that was used in making the case. Here is the G1 spin structure function. You can see that the error bars are already shown on these red plots, and you see the uncertainties so far are quite large. But if we really get the uncertainties that are plotted on this picture, you suddenly know that you will know the value, how the G1 structure function is behaving in this low X region. Fixed target experimental part, the uncertainty is negligible now. You see nothing here. There are data from here that make this very precise. We want to go as much as possible in this region to make that measurement. And once you make that measurement, you will have a precise value of G1 and its slope by that time, because you will measure it at different Q squares, and then come to the same picture that I mentioned to you before, the gluon and quark contribution in the low and high X region. And you can see the higher we go in the center of mass energy, because that allows you to go to the lowest values of X, and the uncertainties, as you remember, the distributions were merging, but they were merging like that to low X. So the lower values of X you go, the smaller the uncertainty will be, and that is depicted in this plot. That you go to 44 GeV, it's right there. At 70 GeV, you go to this intermediate, and at 140 GeV, you go to the smallest one. So that's very natural. There's no magic there. We just have to go and measure it. Yeah, that's what I wanted to show this. Now, over the same 20 years that people have started thinking, the ideas of the three-dimensional structure of the proton have evolved. And now we can place what we see as parton densities in this big picture. And this is what the emerging picture looks like. So there's something called the Wigner distribution, which is a function of X, the X-Weber cane. BT is the transverse distance of a parton, which is hit from the assumed center of the proton, and KT is the transverse momentum of that parton. Yeah, so those are the three things. Remember, BT and KT will have 2 dimensions. So in all, it's not 3-dimensional picture, it's a 5-dimensional picture. Yeah, so it's more complicated than that. But you can integrate over BT, and what you get is the transverse momentum distribution, which is what some of you are experts in, or at least eventually will become experts in. There are some experts sitting here anyway. Yeah, we will measure them using semi-inclusive deep inelastic scattering in the collider regime. We have done it in the past in the fixed target experiment, once we knew how to deal with them. And that's something that you will see in various talks coming in, but that's what we will have to measure. Yeah, semi-inclusive deep inelastic scattering gives rise to the TMDs. If you then integrate over KT, what you get is the spin-independent parton distribution functions that we knew how to measure, we have been measuring. Yeah, so this is how the normal PDFs that we call PDFs are connected to this Wigner distribution through semi-inclusive. If you go the other direction, you go integrate over KT, what you get is an impact parameter distribution. If you integrate over BT, then you should get back the same distribution. Yeah. On this stage here, if you take a Fourier transform, then you start getting into the generalized parton distribution functions of different kind. You will have specialized talks on this in this later talk. But this is also connected to the form factors, the elastic form factors, and the generalized form factors, which are now being calculated also on the lattice QCD. Yeah, so this is the big picture that is emerging, and we will make direct measurements of this. We'll try to make direct measurements of that, and then again, these are low energy electrons. People have measured them, and we'll start making measurements of the GPDs. We'll start filling the holes experimentally for the first time, reliably, hopefully. Eventually, theory and experiment together will develop this picture much better. Yeah? This is important to remember. Theory and experiment really go together on a day-to-day basis in this field, which is another attractive feature personally for me for this field. Okay. I think I've said all of this. What I wanted to emphasize is that the transverse momentum distribution and the space distribution should allow us to start thinking about picture of the proton as a whole, where the momentum and the position become clear. And that, at least as an experimentalist in my mind, I start correlating that with the orbital motion. Theoretically, it might not be as straightforward, but at least you get an intuition that I know that we are going after the entire three-dimensional picture of the proton through such measurements. And that's something that is attractive to us. And here is some simulation of a simple transverse momentum distribution which allows us to, comes out of the semi-inclusive deep inelastic scattering. Now, what is shown here is the electron comes through, exchanges a photon, the electron gets scattered. Yes, that's the inclusive part. But now I'm going to go next step. I'm going to see what happens to that photon. And in this model, I have a quark which is going around like that. And it is hit at that point, and the quark starts coming this way. At the edge of the proton, it picks up an antiquark and becomes a pi plus, in this example that I've shown. Yeah? If I measure a pi minus, if it is pi plus, it is UD bar, remember? Valence quark predominantly is U, so I know that you had a U quark hit looking at the charge of the final state pion. As Marco was saying before, flavor is measured that way. If I see a kaon, I know that strange quark was involved. Or K plus, K minus will give me strange or strange bar. Yes? D quark means I should have seen a pi minus somewhere. And I measure left-right asymmetries, and those, which is what Marco said, were different. Flavor dependence came from that. That has the consequence for mass of the W, as was alluded to in the past. So all of that is in these kind of measurements. Anyway, if our knowledge of the U and D quark distributions is correct, then the high luminosity measurement that we will make will give you these kind of momentum distributions for U and D quarks inside the proton, which is transversely polarized. You can see the evidence of asymmetries that you can trace back to the parton distribution. You measure the asymmetries and trace it back. What does it mean for the U and D quark? And that's something that, now eventually when you become, the whole picture becomes clear, including the position, which might come through these non-violent collisions. This is where Mahatma Gandhi comes in. So why does he come in here? So here is the deeply virtual Compton scattering event. The deeply virtual Compton scattering, the proton remains intact. The photon comes through, interacts with the quark. The quark then emits the photon, a real photon, and remains inside the proton. And experimentally, we were startled at HERA in 2001 to 2003. We would make measurements of the total cross-section, but always missing about 6 to 7%. We didn't know why we were missing it. The reason why we were missing it, because we didn't anticipate that. At 300 GeV center of mass, we didn't expect that 6% of the event, the proton doesn't break at all. We didn't know that. However, that was happening. But the tricky thing was the difference in the angle, the scattered angle of the proton and the incoming of the proton was so small that the proton would keep on going in the beam time direction. There was no detector to measure it. Once we learned from our theory friends that such a kind of event exists, we put detectors very close to the beam pipe in the direction of the outgoing proton, and we suddenly see flashes. That's when we learned that we actually had seen and missed it in the past. And that became called deeply virtual Compton scattering, and now it has been used. So once we discover something, we study it, and now it can be used to study what we want to do. The Fourier transform of this distribution of change in the momentum then allows us to get to the spatial distribution, and those are the kind of simulations that you will get for quark-antiquark distributions. Not only that, we will study the evolution of it. Because I told you EIC is a precision and control machine, you can select events of that kind at different values of Q squared, different values of S. And then you can reconstruct these distributions as a function of X and Q squared. Because you have that control, you can do all of that. So what have I told you in summary? I've told you that this is what we started off doing, but now suddenly, because there is internal motion, I want to do a different experiment. I don't want to break the proton. That's why the non-violence comes in. Non-violent collision, or the Gandhian collision, and I'm going to do the non-violent collision on the watermelon, which is an MRI of this. I don't know why they provide an MRI of a watermelon on the internet, but it helps me make the case. All right, so now, the last one. We told you about the uniqueness of the gluon-gluon interaction. It is colored, and it is particularly high at low X. That's where the range was going. And it was interesting in Ravindran's talk, he was talking about a Gedanken experiment. So here is my picture of what he was describing. And this was not planned, this was already there. So just to tell you. So I have a proton, and there are 3 quarks. This is a cartoon. There's other things in the proton too, but I want to focus some. And then this is the direction of time. And if I ask you what does a proton look like, I do a snapshot of proton, and that is shown here, the blue regime here. That's my experimental measurement. And a question I'm asking you, tell me how many protons or quarks and gluons are there inside the proton. And what is happening as a function of time? The quark is emitting glue, and they come back. This keeps on going. There is a continuous soup of quarks and gluons inside the proton, so that they are radiating, they're coming back, yes? So if I make a measurement and measure the number of quarks and gluons, as he was showing, the number density of F2P, et cetera, towards the end, a result of this might be that I have 3 quarks and I have 6 gluons. I just measured them here, 1, 2, 3, 4, 5, 6, 7, 8, 10 gluons, yeah? But what happens, how does the picture change at high energy? That means I'm now exploring low X. And here is the other, that's my Gedanken Lorentz contracted proton. Now it's at high energy. Now the same thing is happening. However, what has changed? There is a time dilation. That time dilation, the gluons radiate more because they're long-lived gluons, they're time dilated in the strong interaction time scales. And those small x gluons will then turn more into, radiate into more. They're living longer, so they will radiate more. Each one of them will radiate more. And suddenly you start getting more and more glue as you go to lower and lower values of X or higher values of energy. So that's the basic idea of that rise in the F2 structure function or the gluon distribution at the low X. And that is what is being seen in that plot of F2. Now this was mentioned in the Nobel lecture by Frank Wilczek. It says the result is self-catalyzing enhancement that leads to a runaway growth. A small color charge in isolation builds to a big thundercloud. The key word there is isolation. So what he's saying is this 2 will go 4, 4 will go 8, 8 will go, and will it go to that? And I want to mention this part, he used it very carefully. This is the reason why that doesn't happen, because these are colored particles. They're in isolation, they're inside, they're confined. So what happens with confinement? You have something that covers it, and it sort of increases the density. At some point, it starts merging again. Yes, because it's so dense that it starts merging again. And at some point, the evolution into, recombination and birth of the 2 gluons become equal, and that's where the saturated state might occur. And there are people who have studied this. They call them that state of affairs where the gluon density is saturated, colored glass condensate. And they said this might happen, and that's where the slope of this gluon distribution will change. What will change? What will I do? I can make a measurement of F2 at extremely low X of a proton, or I have to use a nucleus and make a measurement of F2 of a lead nucleus and measure that. Yeah? If this is really happening, one of the signals will be this. I'll show you something more a little later. But one of the things is that should change. Yeah? And there are ideas about that. They're called color glass condensate. They've called the authors of this idea. Color is obvious. Condensate because they're spin-1 particles in large numbers. They form condensates. And glassy because they think that the interactions are over the entire volume. You see that the whole nucleus is involved in this kind of a thing. So the interactions are not localized. They're over the entire volume, as was alluded to also in Ravindran's talk later. So this is something that is different, and that's something that we'll have to go after. Now, how do we do that? I already alluded to that, but let me explain again. Instead of a proton, I'll take a nucleus, I'll boost it, and that's my colored boosted nucleus, and I explore it with the same kind of a high energy probe, and then suddenly you have a saturation scale which is proportional to a to the power 1/3, where a is the size of the nucleus, and high energy part comes in X, it's low X. High energy part, the lower the value is X, this is increasing. So the hope is to go to the highest level, heaviest nucleus, and the lowest values of X, highest energy, and see if we can find these changes that happen in the state of the affair. The reason why we think it is possible And if there is a paper, you will probably hear about it next week. There's a paper that came out last week from STAR collaboration where they've seen the first evidence of such a thing. Is that indirect evidence, but there is evidence there. You see for proton in 300 GeV EP, this value of QSA still sits in this very small value. This is lambda QCD, this is 2.5 GeV squared. At the EIC, with the energies that we plan, we can get significantly above it. Whether significantly above is enough, only nature can tell us, but at least we give it a try. Yeah, we give it a try. Another way to measure this, one more method, is that people know about dijet events. You see EP and then the two jets come out. Yeah, one of the proposals, the predictions of this color glass condensate, it's a very highly dense event. Dense objects typically are not good for passing through. So the idea is that instead of two jet events, you will miss one jet. One jet will not be able to come out. Those who are studying quark-gluon plasma, they have studied this same idea. You have a nucleus-nucleus collision, and then the jet passes through, the two jets which are created. One of them gets, it looks like a momentum conservation being lost. It's not really that. It is all lost in the path. And so the simulation shows that, is that EP looks like that. If EA also looks exactly like this, no matter what energy you look at, then you're dead, meaning you don't find anything. However, the simulation, knowing our knowledge so far, or in the model, it says as you go to higher and higher center of mass energy, as means you go into that regime of high parton density, you should see that there's a depression of one of those jets. And if you're lucky enough, you'll see in the EA, one jet is completely missing, if the density is high enough. Yeah, that is one thing. I told you the first one was F2 structure function. Gluon distribution should naturally change. That's purely inclusive signal. This includes the hadron signal. Yes? So it's an addition. They should not be either or. They have to come together. So there should be 3, 4, 5 things that should come and point to the same physics. Should be thresholds on the same energy. Yeah, experimentally, I will not believe only if you see a change in the F2 structure function and nothing of this sort. Yeah, I will look for 4 or 5 things in the same detector to make sure that all of them point to the same thing. And the last one is a beautiful thing. Undergraduates know what diffraction is. You can do diffraction with electron-nucleus collision. Electron is the wave. Look at a solid nucleus of gold or lead or uranium, and this color glass condensate is formed, extremely high density. It's like an opaque cardboard looking at a monochromatic light. And you see these peaks. Now, this is a difficult measurement, but there are simulations that tell you that such peaks should be present in the measurements of the final states in the very forward region. And we'll certainly make designing the detector to make such measurements. Yeah? Okay. I'll go quickly through some of the remaining parton distribution functions in nuclei. We know that there are large uncertainties here, and with EIC, they will go down. They will then could be used to understand nuclei in nuclear collisions at RIC or LHC, but generally the knowledge of that, precise knowledge of that, will be the first time that you will get it at extremely high energy. Last but not the least, as I mentioned to you, you can make control of the nuclear dimension by changing this size of the nucleus and studying where this hadronization occurs. Yeah, we can study that very carefully. That has not been possible for the same reason I mentioned to you in the past. We've never had a target in which you could see all the nuclear fragments come out. Yeah, because we already had solid state targets, even nuclei. There are many things more that you can study, and this is something that Marco was alluding to, that what plays, the TMD's role play in the W production, W mass precisely, and that has very significant consequences. But my claim, our claim, is to see even the precise knowledge of normal parton distribution functions. That will be much better than the HERA. How they impact. There are some studies that are now coming out already, if you look at the literature. What would be the impact of EIC measurements on that? Measurement of alpha S, for example, precise measurement of strong coupling constant. Those are all things that are coming up. When there's a list of things that you can look at, once you have a collider, that's not the only thing that we did. The motivators is what we discussed so far. But there are lots of things you can do here. And some of you might be ending up doing these things. It will be important in their own right. And hopefully you get involved. And then there is also the Electro Week and beyond the standard model searches, which I will not get time at all to talk about. So let me summarize everything now. So there is on the x-axis is the center of mass energy. On the y-axis is the luminosity that I mentioned to you before, from 10 to the 32 to 34. And this is the integrated luminosity in the years of operation. And these are generally the blobs of science, regions where the physics that we have mentioned comes into play. And as soon as we reach those kind of plots start coming out, and making measurements is something that we will be focusing on. Here is the collider that might look like. This is what the injector to the RIC is. That will remain the same. We'll replace one of the rings from the RIC by an electron ring and have collisions in this region 6 o'clock and 8 o'clock eventually. Currently, we are planning to build one detector, and that's going ahead. Hopefully, in the future, we'll have the second one, which will sit there. And that's how the location, the view of the electron accelerator looks like. Those I think I've already mentioned. This is where the machine, the people are telling us that this is the machine delivery, so that luminosities and the center of mass energies are consistent with our physics aim as we have laid it out. Now, it is going to be an asymmetric detector. This is, most of you are theorists, right? Are there experimentalists in here? Not a single one. Oh, there's one. Oh, my friend. Oh, good. So this is, so everyone else should know this. He will learn it anyway. Right? Everyone should learn this. So you have an asymmetric detector. You have a proton beam. You have an electron beam coming. And I have alluded before, you need to go in that direction to make the electron measurements. So electron end cap predominantly goes here. You see that? The scattered electron goes in that direction from low q squared to high q squared. If you look at the hadron, it's the high X hadrons, the medium X hadrons, and the low X hadrons. So hadrons are going everywhere. If that's what the simulation tells you, that's how you start designing the detector. And that's how we started, yeah? Looking at the characteristics of X and Q squared. The homework that I gave you today really goes into the design of the detector, exactly as we did it, yeah? Not in Excel sheets, in root, but the same thing. So that will give you a feel for where the quarks go, where the electrons go, and that's really what we started doing. And that's how the design of the detector comes through. It's in the central part here. And then to see very small variations in the angle of the electron and the hadron that normally go into the beam pipe. How do we do that? We can't block the beam pipe there. So we have to put detectors far, far away. So here is the beam line that goes that direction. And this is 40 meters, 20 meters, 60 meters. And the detectors are embedded into the accelerator ring. Because if there is a change in the small change in the momentum of the proton as it hits, yes, as a function of distance, it will come out more. It will come out of the beam thickness itself or beam radius itself. And we can make those measurements far away. Those who have followed LHC program, our RIG program, we have something called Roman pots, which sit further away, yeah, long, far distance away. Here is the central detector, and in both directions you'll see detectors which are embedded, and this is part of the physics program as well. The three-dimensional view of the central detector that looks like this, I think I'm going to go quickly on this one, but you can see the asymmetry already. The hadron beam comes from that direction, the electron beam comes from that direction, and you can see that there are differences in the hadron side and the electron side. There's particle ID, there is tracking everything on this side, a lot less of particle ID because not much is going in that direction. You need to isolate electrons from hadrons, et cetera, et cetera. That's what it looks like. There's an international collaboration being built around it. You can see India right here. Part of it, there are about 22 institutions. If you don't know which one they are, might be some of them yours are, but look for them and get involved. Not just experimentalists, also theorists, the large group that are getting involved with that. Here is what the collaboration looks like so far internationally. Very large collaboration, a large amount of non-US participation, about 55% is already non-US participation. And the whole interactions are working very well at the international stage. I want to not show this again, this is the last slide, but you've seen this before. What you didn't see in this simulation was what spin was doing, how the quarks were moving in transverse dimension, how they were, if there was an orbital part, we didn't show that yet here. All of that is new. All of that will come eventually in simulations, but before that, it will have to come with the data. Yeah, so that's what the whole idea is. It took a long time. We started, I alluded it that we started thinking about a collider in 2002, and now we are building it. It will get built in about 10 years. We're building the detector now. The data will come around 2032 or so. And it's going to be very exciting because the first time a new collider is going to come about is a high luminosity EP-EA collider. There will be up to 2 hermetic detectors, out of which one is now funded. The second one will be hopefully funded in the next 5 to 10 years. And we have, some of us have started working on that already. There is a high interest. But all the early careers, this is really a machine for you. Your careers are going to be built on this machine. And it's a QCD machine, so there will be things to measure. Yes. Get involved now. It's a real opportunity. Thank you very much. I miraculously finished in time. Yes, questions? Otherwise, there's no lunch. I already seeded some questions. Come on. I seeded questions in my, yes.
So, yeah, very nice talk. So small confusion when you were discussing about this collision and jets coming out. So you mentioned that one of the jets we may not detect it, right? So why is this asymmetry? I mean,
because one of the if the claim is correct that this color glass condensate or a saturated state of proton is being formed, it is so dense that the jet doesn't have the energy to transverse through it.
so why not in both directions? I mean,
It could be, chances are, but normally what we have seen, the current simulation or understanding in heavy ion physics is that typically these collisions are happening peripheral in the nucleus. And so one of them gets blocked, the other one comes out. And the other one, and there is also measurement bias. I'm glad you asked this question. If both jets are submerged, I don't even know that happened. So I'm biasing my event sample by looking for one jet. And I look for, when there is one jet, I know for sure from momentum conservation that others should exist. So it's a simple bias that comes in the measurement itself. Yeah?
thanks.
I have a follow-up question to that. So what is the X, Bjorken X value for this measurement? You expect?
I don't care. It has to be in the low X region because this is where the color glass condensate or saturation state exists.
Yeah, exactly, because otherwise you would have some nuclear effects also, right?
Yes, absolutely. But there will be no exotic in the low X, in the high X part, is what, I mean, we know the exotic part, the high X part already. We have seen it. If you start seeing something like that there, that would be an interesting question to ask as to why that happens there. But it would probably, the proponents of it would argue that means that this effect is starting at much higher X than anticipated. But we would have seen it in some way or the other. We have not seen it. In PA, so what we have done so far is a poor man's EIC. We have done PA or DA and looked for these signals. And they're not clean because there is no, the kinematics is not that precise, the control is a lot less. But as I mentioned, there is a paper now that I just got last week, actually flying here, that there is a paper from STAR that says they have seen these pion production in one direction, which shows the sign that is mentioned, that they can correlate with the potential existence of high gluon density in a nucleus. So it tells you that there is something. But as I mentioned to you, as an experimentalist, I want to see all 5 of those signatures come through, because this is an important enough measurement.
Can you comment on the theoretical and experimental uncertainties on the G1 structure, G1 spin structure function at low x?
Yes. Sangwa, are you going to do this? No? So,
Sorry, I cannot hear.
no, I can comment and we can discuss more detail. So theoretical uncertainties in G1 spin structure function. So we measure them. We measure the A double spin asymmetries, A parallel, yeah? From there we calculate G1, experimentalist. To go from A to G, there are certain things that we need to do. We have to do the radiative corrections for event by event.
Right.
Those we have to do. We have to do corrections based on our acceptances. And then we have to use a R and F2 parameterizations to go from there. There are inherent uncertainties on that one. So when we calculate, we fold all of those uncertainties in. And when you see a G1 with an uncertainty from experiment, those uncertainties are already counted in addition to the statistical uncertainty.
Okay.
Now, if you mean, now I want to do the evolution and get the uncertainty on gluon distribution, there I start looking at evolution of G1 using the Alterelli-Parisi equations. We fit them to the global fit. And the global fitting involves other theoretical uncertainties, because then you have to decide which data to select. Where is the perturbative regime where this formalism really works? And there are differences. You can go to Q squared of 1, Q squared of 4, Q squared of 20. Historically, people will not accept any data below Q squared of 20 as being perturbative. Now, if you do the same thing for our spin structure functions, there are no data at all. You can't do anything. EIC will provide them.
Right.
So we will do studies where we will put limits on 20 GeV or 4 GeV. See if there are differences that come out in the final result. If there are no final result, the studies that we have followed in the HERA part, we learned that by going from 20 to 4 GeV, we didn't see any differences in our final estimates of gluon distribution, which meant that we were in the perturbative regime.
Right.
And we kept on going down, and we did such systematic studies will have to be measured, have to be done. Yeah.
Have to be done in theory.
Theory with the global analysis, typically.
Okay.
Yeah. In the theory, I would expect that the precision that EIC will demand, you will have to push the calculations to next to leading order.
So the perturbative framework could still be valid.
Yes, of course. I don't have any uncertainty about that. But the uncertainties on the theory side will not be enough to really decipher things from the experiment, which means that you have to go to the higher level of calculation.
That I understand.
Yes.
So it would be something like computing radiative corrections to polarized CDs?
Correct, but that's a different thing. But I'm talking about perturbative calculations, the fitting. So all the fitting that we have done so far is simply NLO.
Yes, yes.
And radiative corrections is a completely different affair. You're right, we need to make those, but at least I have not seen that in the EP, we will be limiting it. Maybe some regions I might be. For the EA part, we are dead in the water. If you know how to calculate EA radiative corrections, that's a major project that we need to have. Right there, we are trying to get theorists to get involved with these calculations. So there are real dire need for that.
But even for EA, is there any valid factorization theorem that could help us calculate perturbatively, or is there
calculate what? Radiative corrections?
Yes, yes.
The radiative corrections, I don't think have issues with factorization. You theorists can correct me.
Doesn't?
That is correct, right? So those issues don't come in there. It is simply calculation of a multi-nucleus. So you have an electron coming in and you have a z squared effect. So the radiative correction goes as z to the power 2.
Right.
You have a proton, z to the power 2 is 1. You have a lead nucleus, now you have a huge z. Now every thing that you calculate for radiation has to incorporate that. It was never needed so far, so nobody has calculated them.
Okay.
So that is a real need. There again, I think the NLO and NLO calculations are needed, but that's not in the theory or factorization part, only simply in radiative corrections.
Well, there is the...
Should be on.
There is the formalism by developed the JLab to incorporate radiative corrections into a factorization theorem.
I don't know that, but okay.
Yeah.
I mean, something reliably has to be figured out and tested, yeah, before we actually go in there. But it's a major problem.
I'm referring to Zhang Wei Chu papers. And basically, he developed a formalism to calculate these radiative corrections in order to get to a factorized expression at the end. Because in principle, this would break your factorization. But it seems that it's possible to still build a factorized formalism for that, including the fact that you have z-squared Coulomb corrections when you hit very charged in a target which is rich of protons.
Rich in protons.
Right.
Yeah.
Thank you.
But good question. I mean, yeah, this is something that we have to worry. Actually, I can tell you in the DIS 2023, which happened at Michigan State University in April or so in 23, you should go to that webpage and look at the last talk. Last talk of that conference was looking into the future. It was given by Daniel de Florian, and where he argued for EIC era how theory is lagging behind in calculations at NLO. It's a beautiful talk. You should look at this. It's a non-technical talk, but makes the case beautifully. So if you have not seen it, I highly recommend it. Yeah.
Okay, so if there are no further questions, let us go for lunch, and you are free to catch the speakers during lunchtime and have more discussions.
Good.